In this video, we're continuing to solve integrals using trigonometric substitution. Okay, so when we look at this integral, you can first think about doing a u substitution, but even if we could do a u substitution here, we're really just practicing trig substitutions, but we couldn't even do a u substitution here anyway. All right, and so now we look at this integral, we look at any integral, and what we're looking for when it comes to trig substitutions, we're looking for expressions that are in the form a squared plus or minus x squared or x squared plus or minus a squared. We'll be able to transform expressions like that into simpler expressions that are trig functions. In particular, this is most powerful if you have like a square root or even an even root. If you have an expression like that under a square root, then the trig substitution eliminates the square root. But it's not like you have to have a square root to apply a trig substitution. It's really more about the a squared plus or minus x squared plus or minus a squared expressions. And so you're looking for an expression like that. Either it's an expression that's explicitly in that form, that a squared plus or minus x squared or x squared plus or minus a squared form, or an expression that you can transform into that form. So here, just looking at this, we don't see any, an explicit a squared plus or minus x squared or x squared plus or minus a squared. But here, if we look at this and we think that we can transform this into something like that. So if we said that u was equal to 5x, okay, then u squared is equal to 25x squared. And so this 9 minus 25x squared is equal to 9 minus u squared. And so now this is in the form a squared minus x squared. Well, but x is u in this situation. And that we could work with this with a trig substitution. So here are the three different situations. And this is referring to specifically we have it's different ways of combining a squared and x squared. A squared minus x squared, a squared plus x squared minus a squared. And it includes the square root because that's the most common situation. But again, you don't have to. A trig substitution is more about the combination, the a squared plus or minus x squared plus or minus a squared. That's what we're making the substitution for. But again, it's just this trig substitutions are most powerful when you have an expression like that contained under a square root. Okay, but so here this is the form we've got. We've got 3 squared minus u squared. And so in this case, we would make the substitution that u is equal to a sine theta. U is equal to 3 sine theta. And so if we say that u is equal to 3 sine theta, then, okay, but what is u? U is 5x. So x is equal to 3/5 sine theta. And so this is the substitution we want to make. As far as subbing into this, to apply the trig substitution, we want to make this substitution. X is equal to 3/5 sine theta. Okay, so we're going to say that x is equal to 3/5 sine theta. And just keep in mind, especially since we're doing a definite integral, that when we make this substitution, we're restricting the domain of sine theta to be minus pi over 2 to pi over 2. Because the sine theta needs to be a 1-to-1 function to do this. It needs to have an inverse. And so similar to how we did to define inverse trig functions, you have to restrict the domain. Okay, so in this case, then dx is equal to 3/5 cosine theta d theta. Okay, so the point of the trig substitution is that when we plug it in here, it's going to greatly simplify this. So we're going to get 9 minus 25 times, so 3/5 sine theta squared is going to be 9/25 sine squared theta. So we've got 9 minus 9 sine squared theta. Okay, 1 factoring out of 9. All right, so 1 minus sine squared theta is cosine squared theta. So this is 3 cosine theta. And usually we would put an absolute value around the cosine theta, since, you know, if for certain values of theta, cosine theta could be negative, but there's no negative value would come out of this, right? A principal root symbol in cosine squared, but we can remove the absolute value because of the domain restriction. The domain restriction, we're only going to have positive values of cosine. So like the domain was minus pi over 2 to pi over 2. If you think about the unit circle cosine is only positive in that region, in that range. Okay, so yeah, there you go. So this, with the substitution, this becomes 3 cosine theta. So we've got 3 cosine theta, and then 9/25 sine squared theta, and then dx is 3/5 cosine theta d theta. All right, now let's update the limits of integration. So to do this, I would recommend doing this. It makes it a lot easier. So it's a little different with the trig substitution, since we're doing it's the substitution rule in reverse. And so here x is equal to 0. And now we need to solve for theta. So that we have inverse sine theta 0 is 0. Okay. Now let's see. We got 0.6 is 6/10, which is 3/5. So 3/5 is equal to 3/5 sine theta. So that's going to be, when is sine theta equal to 1? Pi over 2. All right. So let's see what we've got here. This cancels. This cancels. All right, so 9/5. We could bring out a 9/5. And then sine squared theta d theta. Okay, so now we know how to solve if we have a sine by itself or a cosine by itself to any power, we can solve that. And if the power is even, we use I think it's the half angle identity they call it. So this is 1/2 1 minus cosine 2 theta. All right, so okay. This is, so it's going to be theta minus, and then the integral of cosine 2 theta is 1/2 sine 2 theta. Okay, and then we're going from 0 to pi over 2. All right. So if we plug in 0, this entire term is 0. We plug in pi over 2. So it's just, yeah, we're going to evaluate this at pi over 2. So pi over 2 minus 1/2 sine of pi. Sine of pi is 0. So this is 9 over 20 pi. Okay, now the answer key is saying it should be 9 over 500 pi. And so where did I mess up? So it's got to be somewhere in here. Dx is, that's right. X squared, we get 9 over 25 in the numerator. And then in the denominator, you get just a 3. So 9 over 25 times 1 over 3 is 3 over 25. And then times dx times 3/5. Okay, there we go. This is 9 over 125. So I messed this up here. All right, 9 over 125. Over 125, then 9 over would be 125 times 2 is 250. All right. Okay, now 250 times 2 is 500. So 9 over 500 pi. All right. There we go. Okay, so just looking at this, how can you solve this? There's no u substitution. This is hard to solve, right? But we can see that there's something we can, under a root here, that we could put in the form of like an x squared plus or minus a squared. So if we say x squared plus 2x plus what? If we want to make this into a perfect square trinomial, x plus a squared is x squared plus 2ax plus a squared. So in this case, 2a is equal to 2, a is equal to 1. So we'll do like that, right? We haven't changed the expression. And so what we've got is x plus 1 squared minus 1. Okay, now if we say that u is equal to x plus 1, then we've got u squared minus 1. U squared minus 1 is this form here. So we want to make the substitution that u is equal to secant theta. So if we say that u is equal to secant theta, u is equal to x plus 1. So x is equal to secant theta minus 1 is the substitution. So x is equal to secant theta minus 1. Dx is equal to secant theta tangent theta d theta. Okay, so x squared plus 2x, if we make the substitution, x squared is secant squared theta minus 2 secant theta plus 1, and then plus 2 secant theta minus 2. So minus 2 secant theta plus 2 secant theta, so we've got secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta. So this is tangent theta. Okay, so we've got tangent theta, and then dx secant theta tangent theta d theta. So we've got tangent squared theta secant theta d theta. Okay, now we don't have an odd power on the tangent or an even power on the secant, so we're going to have to just manipulate this to see what we can get. Tangent squared theta is secant squared theta minus 1. Okay, so we've got okay, so this is 1/2 secant theta tangent theta plus natural log of the absolute value of secant theta plus tangent theta, and then minus natural log. This integral is natural log of the absolute value of secant theta plus tangent theta. And so if we distribute the 1/2, then what we're left with is okay. So now let's draw the right triangle. Okay, so we've got secant theta is equal to x plus 1 over 1. Okay, secant is the opposite of cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. Okay, now if this is z, then we've got z squared plus 1 squared is equal to x plus 1 squared. So z squared is equal to x squared plus 2x plus 1. Okay, and then so z is equal to square root of x squared plus 2x, okay? All right, so we've got 1/2 and then secant theta. All right, tangent theta is opposite over adjacent. Okay, secant theta, again, is x plus 1. And then okay, so we've got and there we go. That is the integral. All right, if we look here, the first thing we can think about is, can we make a u substitution? But if we said u is equal to 1 minus x to the 4th, that's not going to work. And so what we're looking for here is the potential for, if we see like something in the form of an a squared plus or minus x squared, or x squared plus or minus a squared, then we can consider a trig substitution. And this is particularly helpful if we have that expression under like a square root, because the trig substitution will eliminate the square root. And so we don't see, we see a 1 minus x to the 4th. So that's close to like an a squared minus x squared, but it's not quite that form. And so we're looking for an expression that's either already in that kind of form or that we can put into that kind of form. So, all right, 1 minus x to the 4th is 1 minus x squared squared, right? So if we say that u is equal to x squared, then this is 1 minus u squared, that is in the form that we're looking for. So if we come to the three possible trig substitutions that we can make, we see that that is this form here. We have a squared minus the variable squared, where in this case a is 1. And so we want to make the substitution that the variable is equal to 1 times sine theta. So we want to say the variable u is equal to, we're going to do 1 because it's 1 squared minus u squared. So just sine theta. Okay. Now u is equal to x squared. And therefore, the substitution that we want to make is that x is equal to sine theta, the square root of sine theta. So we say that x is equal to the square root of sine theta. Therefore, dx is equal to cosine theta over 2 square root of sine theta d theta. Okay, and so if we, the whole purpose of the trig substitution is it's going to simplify this. So 1 minus, and this is going to be the square root of sine theta to the fourth is sine squared theta. 1 minus sine squared theta is cosine squared theta. There we go. Okay, so now we can make the substitution. We've got, let's do this. Okay, and then dx is so these cancel, and we're left with 1/2 cosine squared theta d theta. 1/2 integral cosine squared theta d theta. Okay. Okay, to solve a cosine squared theta, we need to use the identity that cosine squared theta is 1/2 times 1 plus cosine 2 theta d theta. So 1/4. Okay, so plus so this is 1/4 theta plus the integral of cosine 2 theta is 1/2 sine 2 theta. Okay, so we've got, okay, sine 2 theta is 2 sine theta cosine theta. So, okay. So we've got 1/4 theta plus sine theta cosine theta plus c. All right, so now let's draw the right triangle. All right, so sine theta is equal to x squared divided by 1. Sine theta is equal to opposite over hypotenuse. Okay, so if this is z, then z squared plus x squared is equal to 1 squared. So this is the square root of 1 minus x squared. All right, so, well, okay. Theta is equal to inverse sine x squared. Sine theta is equal to x squared. And then cosine theta is equal to adjacent over hypotenuse. Okay, so 1/4 inverse sine x squared plus 1/4 plus c. Okay, I wanted to do this problem just to illustrate that the square root is not married to trigonometric substitution. So here we don't have a square root. Okay, but what we're going to do is we're going to put this into that x squared plus a squared form. So x squared minus 2x. Okay, so we've got x plus a squared so 2a okay, so we've got 1. So this is x minus 1 squared, and then minus 1. So x minus 1 squared plus 1. So now if we say that u is equal to x minus 1, then we've got u squared plus 1. So we have that's here, x squared plus a squared. So we want to say that x is equal to, or u is equal to tangent theta. So u is equal to tangent theta. But u is equal to x minus 1. So x is equal to tangent theta plus 1. So x is equal to tangent theta plus 1. Therefore, dx is equal to secant squared theta d theta. Okay, so x squared minus 2x plus 2 is equal to what? Tangent squared theta plus 2 tangent theta plus 1 minus 2 tangent theta minus 2 plus 2. Okay. Tangent squared theta, well, these go away, plus 1. This is secant squared theta. Okay, so we've got secant to the 4th of theta, and then, well, let's do that first. So we got x squared is tangent squared plus 2 tangent theta plus 1, and then plus 1. So tangent squared theta plus 2 tangent theta plus 2 all over secant to the 4th theta. And then dx is secant squared theta d theta. So all right. So we've got an even power of secant, but that's not going to help us here because, typically we would say that u is equal to tangent theta. And then since du is equal, in that case, is secant squared theta d theta, we get rid of the secant squared theta d theta, and we're left with a function of tangent. But this is different because we've got the secant squared in the denominator. So, okay, let's do this. It's nice that we can separate this out into 3 separate integrals. So tangent squared theta over secant squared theta. All right, so we've got sine squared theta over cosine squared theta times secant is cosine, so this is cosine squared theta. There we go. So this is tangent squared theta over secant squared theta is sine squared theta. Plus, okay, tangent theta over secant squared theta is sine theta cosine theta. Okay, and then 1 over secant squared theta is cosine squared theta. Okay, so sine squared theta d theta is, or sine squared theta is, so take out the 1/2, 1 minus cosine 2 theta. So we've got so 1/2 theta minus 1/4 sine 2 theta. Okay, now let's do the cosine squared. So we've got 2, we'll take out a 1/2, and then we've got, it's 1 plus cosine 2 theta. So theta, or no, it's plus. Okay. Now, so if we say that here that u is equal to sine theta, then du is cosine theta d theta. And so we've got u du. This is just u squared sine squared theta. So this plus this plus this we've got 1/2 theta minus 1/4 sine 2 theta plus theta plus 1/2 sine 2 theta plus sine squared theta. Okay. So this is 1/2 plus 1 is 3/2 theta minus 1/4 plus 1/2 is 1/4. Okay, now sine 2 theta is 2 sine theta cosine theta. There we go. Okay, now so we've got tangent theta is equal to x minus 1 divided by 1. Tangent theta is opposite over adjacent. Okay, so the hypotenuse squared is equal to x minus 1 squared plus 1 squared. X squared minus 2x plus 1 plus 1. So okay, so, well, first of all, theta is equal to inverse tangent of x minus 1. All right, now sine theta is equal to opposite over hypotenuse. Okay, and then cosine theta is equal to adjacent over hypotenuse. There we go. So we've got 3/2 inverse tangent. Okay, and then 1/2 sine theta cosine theta. So we've got 2x squared minus 2x. Okay, now sine squared theta. Okay, now what we could do is we could do that, and actually I'm missing a minus sign here. So there'd be a minus sign here. All right, now what is x minus 1 plus 2 times x minus 1 squared? So x minus 1 plus 2, and then x squared minus 2x plus 1, x minus 1 plus 2x squared minus 4x plus 2. So 2x squared minus 3x plus 1. Okay, so we could say minus, well, no. Well, okay, no, that'll be, let's see, hold up. So this would have a minus sign out front of this. Yeah, so, okay, that's fine. So we could say like that, plus C.